What is the Kelvin scale's role in quantum computer cooling? Imagine trying to keep something incredibly tiny and fragile at a temperature colder than anything you've ever experienced. That's exactly what scientists do when they work with quantum computers. The Kelvin scale is the key to measuring these extreme temperatures. It starts at 0 Kelvin, which is the point where atoms stop moving entirely. This is known as absolute zero and is minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. Quantum computers, especially those using superconducting qubits, need to operate near this temperature to work properly. Superconducting qubits are the heart of many quantum computers. They rely on materials that become superconductors only at very low temperatures. When cooled to near absolute zero, these materials allow electrical current to flow without resistance. This resistance-free flow is essential for maintaining the delicate quantum states that enable quantum calculations. If the temperature rises even slightly, thermal vibrations can cause qubits to lose their quantum information, a problem called decoherence. To reach these ultra-low temperatures, scientists use cryogenic systems. These systems include devices called dilution refrigerators, which can cool down to around 20 millikelvin, that's 20 thousandths of a Kelvin. These refrigerators work by mixing two isotopes of helium, helium-3 and helium-4, to create a cooling effect. The Kelvin scale helps engineers precisely measure and control these temperatures, ensuring the system cools gradually and avoids thermal shocks that could damage the hardware. The role of the Kelvin scale doesn't stop at measurement. It guides the entire design of cryogenic systems. Each stage of cooling reduces the temperature step by step, from tens of Kelvin down to millikelvin levels. This careful process ensures the quantum processor remains stable and noise-free. Maintaining these temperatures allows qubits to stay in superposition and entangled states longer, which is vital for complex quantum calculations. In practical terms, knowing the temperature in Kelvin helps researchers set exact parameters for their cooling systems. It also helps them troubleshoot and optimize the cooling process. The lower the temperature in Kelvin, the less thermal energy there is, and the better the qubits perform. This precise temperature control is what makes quantum computers possible and reliable. So, in the world of quantum computing, the Kelvin scale isn't just a way to tell temperature. It's a vital tool that shapes the architecture of cryogenic systems. Without it, maintaining the ultra-cold environment needed for quantum hardware would be nearly impossible. The Kelvin scale is the foundation that keeps these tiny, powerful machines running smoothly at the edge of absolute zero.